Okay, so here I'm answering some questions, exam practice questions for Topic 7 Magnetism. And what I'm going to do is I'm going to heavily lean on the revision guide in order to help me answer these questions, just so that we can see how we can, again, use the revision guide to help our revision for exams. Okay, so question 1 is a question about electromagnets. In terms of the revision guide, that means I know I'm looking at page 228 of the revision guide. And it shows me 3 electromagnets. And it says there's an experiment where the student has different numbers of turns of magnets and has paper clips hanging from the end of the electromagnet. The electromagnet is made from a nail, which is an iron core with some wire wrapped around it. Okay, and it says that's the maximum number of paper clips that can be hung from each of the electromagnets. Complete the conclusion that the student could make from the investigation. So where there are more paper clips, this means that the electromagnet has a stronger magnetic field. So that means that the magnetic field of B is equal to the magnetic field of C. Why? Because both of them have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 paper clips. So the strengths of these magnetic fields are the same. And then on here I've got 1, 2, 3, 4 for electromagnet A. So the strength of electromagnet A is less than B and C. Okay. So what's the difference between A, B and C? Well, B and C have got more turns than A. So what can I say? Increasing the number of turns wrapped around the nail will do what to the strength of the magnetic field? Well, we see when it goes from 20 to 30 turns, the magnetic field becomes stronger. When we don't change the number of turns, the magnetic field doesn't change. So increasing the number of turns will increase the strength of the magnetic field. And this is described here. We said that the in here we can increase the strength of the magnetic field by wrapping the wire into a coil, because they all line up, the field lines line up together. So by adding turns to my coil, I will increase the strength of the magnetic field. Which 2 pairs of electromagnets should be compared to make this conclusion? Well, we are comparing ones that are different, A to B. So we can compare A and B. But we also see that we need to be sure that it's not something else causing the change. So we compare where the number of turns are the same, and we find that the magnetic field doesn't change. And then the final question, suggest 2 variables the student could con. So the last question is to suggest the 2 variables the student could control in this investigation. So to answer this question, we need to ask ourselves, what makes the magnetic field stronger? So I go to my revision guide, and it will give me some information about this. So first of all, the magnetic field produced around a wire, it changes with the current. Okay, so the larger the current through the wire, the stronger the field is. So the first thing I can do to change the magnetic field is the current. If I increase the current, I increase the strength of the magnetic field. I can do what I'm saying in this experiment, which is increase the number of turns in the coil. That increases the strength. And then the last thing is, it says in my revision guide, I can increase the field strength even more by putting a block of iron. Okay, by having an iron core. Right, now, so these three things will affect the magnetic field. This is the one that I'm interested in the experiment, the number of turns, which means I have to be sure that these two don't change, because that could change the strength of the magnetic field. So what should I control in the experiment? I need to control the things that could change the magnetic field strength. So that is the current, and I need to have the same iron core, the same nail for each of them. Now, in the next part of the question, it tells us that the cell is swapped around to make the current flow in the opposite direction. So what we can see is that in the first orientation of experiment A, we see that the current is traveling clockwise around the circuit, so the positive side of the cell is here. And then it says in part B, we've swapped around the battery, so the positive terminal is here, and the current is now going anti-clockwise. What is the maximum number of paper clips that can now be hung from a line, in a line from this electromagnet? So we can go back to what we previously said. What are the things that make the magnetic field stronger? Well, for the iron core, has the iron core changed? So the iron core is the same, so that won't change the strength of the magnetic field. It will be the same as before. The number of turns, still 20, so the number of the turns is the same, so that won't change the magnetic field strength. And what about the currents? Well, we have the same cell, it's just turned around, so the size of the current is the same. The direction has changed, but the size of the current is the same. Right? And those are the three things that can change the magnetic field strength. And what we're saying is they are all the same. So if they're all the same, that means we will end up with the same number of paper clips, which is 1, 2, 3, 4. So the answer will be 4. So we have the same number. So what's all that's changed is the direction of the current. So the size of the current has not changed, only the direction, which does not affect the strength of the magnetic field. Okay, and then finally it says electromagnetic A is changed to have only 10 turns of wire, suggests the maximum number of paper clips. So we saw that increasing the number of turns increased the number of paper clips we could pick up. And we saw that basically 20 turns, I had 4, 30 turns, I had 6. So for every 10 extra turns, I'm going up by 2. So that would suggest that if I have 10 turns, I would have had 2 paper clips. Okay, question 2. It shows us this toy using ring-shaped magnets. It tells us the magnets can move up and down the rod, but the ring magnet B appears to float. So that means, remember, B is going to be pulled down by gravity. So there must, if it's floating in midair, there must be a balancing force. So if I was to draw this out here as the free body diagram, this is my magnet B. Its weight, which is equal to mg, will be pulling it down, which means there must be an equal force upwards for it to be balanced. So how could that force, where is this force coming from? This will be the magnetic repulsive force between A and B. So A is going to be pushing magnet B upwards, and for there to be a repulsive force, the poles have to be the same, which means that is the North Pole there and the South Pole there. Okay. What would happen if the magnet was turned upside down? Well, now we would have unlike poles, so that would mean that the magnet B would be attracted to magnet A. Okay. Now, the next question is moving on to the magnetic field around a current carrying wire, and it says we've got 4 compasses around a wire. Here the switch is open, so there is no current. Okay, and notice all the compasses are pointing in the same direction. That means that north on the Earth is in that direction, because the compass will point north when it's not near to a magnet. Explain why all the needle points, or the needles point in the same direction. So I'm going to use the words coming from the revision guide to answer this. So when they're not near a magnet, they always point north. This is because the Earth generates its own magnetic field. Okay. As they are not close to a magnet, all the compass needles point north. And why is that? Because, just remember, 2 marks, the Earth has a magnetic field. Then the next question, we now have closed the switch, so now there is a current, and it says the compass needles change direction, draw the arrowheads. So here we're turning to page 228. We see that when there is a current in a wire, the magnetic fields are in concentric circles around the wire, and the direction is given by the right hand thumb rule, where thumb goes in the direction of the current and fingers curl around to show the direction of the magnetic field. So we can do the same thing here. It shows us the current is going upwards, which means the magnetic field is anti-clockwise. Okay, so it's going around that way. So that means that we can show the arrowheads will be in the anti-clockwise direction. What would happen to the direction of the compass needle if the current was reversed? Well, this time the current would be going downwards, so now they would be going in the clockwise direction. So we could say that the needles would point in the opposite, let's put in brackets, clockwise direction. Okay. And then we're moving on to the bottom of page 228 to talk about a coil. So here we have a coil in a circuit, and we're asked to draw the magnetic field due to current in the circuit. Okay, so when we draw the magnetic field around a coil, we can draw it in the same way as if we had a bar magnet. So when I'm going to do this, I could start by just reminding myself, if I had a bar magnet like this, what would the magnetic field look like? So in a bar magnet, the magnetic field lines, they loop around going from north to south. So I can use the same approach, just imagining the coil is like a bar magnet, and I can draw the magnetic field. So here we have my magnetic field around the coil. So we see that the lines are going from north round to south, and they're looping round in the same way as they do with the bar magnet. The only difference is we have to show the field lines going through the center of the magnet like this. So the field lines form a loop, and here we can see them going through the center, which we don't see with the bar magnet. So that's the only extra bit we would have to add. So question 3, and it starts off again with a question about a bar magnet, where we need to draw the magnetic field around the bar magnet. We then need to be able to describe how we could plot the magnetic field around the bar magnet using a compass. Okay, so this is all described on page 227 of your revision guide. At the top it describes the magnetic field around a magnet, including a picture of the magnetic field around a bar magnet, and this section describes that experiment using compasses to show the magnetic field around the magnet. Okay, so using the revision guide, I can answer this question. So here are parts A and B for that question. In part A, we have the magnetic field, and it is important to show that the lines loop around, starting from the North Pole, going to the South Pole, and you need to add the arrows both at the top and at the bottom. And it's a good idea just to draw in 2 of these loops at the top and at the bottom. Then for the compass, to plot using a compass to plot the magnetic field lines around a bar magnet. And this answer has come essentially from the revision guide, again, because that's our best guess to what might be on the mark scheme. So we have place the magnet on plain paper and draw around it, marking the poles. That's so that you can remove the magnet and put it back. Place the compass close to a pole. Mark the direction of the compass needle using a dot. Move the compass to line up the tail of the compass needle with a dot. Mark the position of the tip of the needle with a new dot. So this is what we're showing. We start with the compass close to a pole, and we put a dot at the tip of the needle, which is what we did here. We then move the compass so the tail of the needle is lined up with where our dot was, and we mark the new position of the tip of the needle, and we continue doing that, so we end up with a series of dots, which we then join dot to dot and put an arrow in the direction to show the direction of the magnetic field line, north to south, or the direction of the needle of the compass. We then put the compass into another position and do the same thing again. Okay. We repeat until the compass reaches the second pole and draw the line with the dots, as said, and then we repeat for different starting positions until we have a picture that looks like part A. So part C, the compass needle. Why does a compass needle move and place near to a magnet? The compass needle is a small bar magnet that can rotate. So the north pole of the compass needle is attracted to the south pole of the bar magnet. So what can we see here? If I've got a bar magnet, this is my needle. The arrow is at the north pole. So here's the north pole. The south pole of the compass would be pulled in this direction, and the north pole is repelled by the north pole. So the arrow will end up pointing in this direction. When we come close to the south pole, the north pole of the compass magnet, called the needle, will be attracted to the south pole, and the south pole of that compass needle is repelled, so it ends up pointing in this direction. Part D, iron is magnetic material. Which of the following are also magnetic material? The answer is cobalt. The other material we need to know is nickel, but that's not given here. Note that not all metals are magnetic, so copper, steel and zinc, all metals not magnetic. This last section, I think we don't need to go through that. That's for a more It's for an old spec question, but just to give you the information, but you won't have to know this for the exam. Two pieces of evidence that show the Earth's magnetic field is changing. The poles, the North Pole is actually changing position, it's moving. And geologists can see that in the past, the magnetic field of the Earth actually reversed, so the poles swapped around. Why might that have happened? It's changes in the Earth's core due to the movement of molten iron in the Earth's core. So I've answered that because it might be of interest to you, but it's unlikely that this question will come up in an exam. So this is question 4, and it's about the electric motors. So this is on page 230 of the revision guide. It says the left-hand rule, so Fleming's left-hand rule can be used to identify the direction of the force acting on a current carrying conductor. This is where we use our fingers and our thumb at right angles. First finger is the direction of the magnetic field, second finger is the direction of the current, and our thumb is the direction of the force of the movement. Okay, so use the words to label. So we've got the first finger, that is the direction of the field. The second finger is the direction of the current, and our thumb is the direction of the force. It then says we have an electric motor, and draw an arrow on figure 2 to show the direction of the force acting on this piece of wire. So we need to remember that in a magnetic field, the field always goes from north to south, so it's always in this direction. And we're going to use the left-hand rule to work this out. So the field is going in this direction, okay? The current is going in this direction, up the page, which means that the force is downwards into the page. So the force is downwards, okay? It then says suggest 2 changes that would increase the force acting on the wire AB. This is where, again, physics is very useful when it uses equations for this type of question, because it's then easy to see what it is that will affect something. So here the force is equal to the magnetic field strength times the current times the length of the wire. So if I increase any of these, the magnetic field strength, or if I increase the current, or if I increase the length of the wire, that will increase the force. So 2 changes to increase the force. Well, I can't really change the length of the wire, so that leaves me only with 2 possible things. And that is to increase, and notice you have to say increase the strength of the magnetic field. That's the B. Or increase the current, which is the I part. And then we had suggest 2 changes to reverse the direction of the force acting on the wire. So if we think about Fleming's left-hand rule, this is the direction of the force. There are only 2 other things here. One is the direction of the field, the other is the direction of the current. So if I was to change the direction of the current, look what happens, that changes the direction of the force. And if I change the direction of the field, but I keep the current going in the same direction, so the field would go that way, the current this way, that means that the force will be downwards. Okay, so in other words, when the field was that way and the current was that way, the force was up. So that's field, current, and force. So if I rotate all of this, I keep the field in the same direction, but I send the current that way, that means the force would be downwards. And again, if I had the field, and now I flip this over, so I keep the current going in the same direction, but I rotate it so that the field is in the opposite direction, then I would have the field, the current, and the force would be downwards. So I can reverse the direction of the magnetic field is one option, or I could reverse the direction of the currents. Right, and moving on to part C. Yep. So this is a really typical question where they describe some experiments, give us some results, and we need to analyze the results. So it's all about a motor used to lift a mass. They've changed the power to the motor, so for different inputs, recorded the time to take the mass and calculated the output power of the motor. So here's the input power here, and here's the output power. Okay, so the result for test D is anomalous, and it asks us to calculate the efficiency of the motor. Okay, so here I'm going to do all 4 steps. I've got a calculation question, so I need to make sure I'm doing all 4 steps. And I've got the input power for D is equal to 80 watts. The output power is equal to 120 watts. And I'm looking for the efficiency. Okay, efficiency is equal to useful output power divided by total input power. So that would give me that the efficiency, putting the numbers in, is equal to 120 divided by 80, which is equal to 1.5. Note there's no units for efficiency. I could multiply this by 100 to get it in as a percentage. So the efficiency is 1.5. And if I wanted to write that as a percentage, I would multiply by 100 for 150. Comment to your answer on, so they're saying something is odd about this. Well, we can see the output power is bigger than the input power. Now you could say it that way, or we can say the efficiency is greater than 1 or greater than 100%. Okay, so why is D an anomalous result? Well, we know D is an anomalous result because we can't have an efficiency that's greater than 1. So what might have caused this to happen? What could be the reason for us having this problem? So it's unlikely that the efficiency, the power measured in as chain, is incorrect. The work done is the same as all the rest, so that seems fine. So it's likely that this is the problem. So what might be the reason for this anomalous result is the recorded time taken is too short. And that could be because the person using the stop clock stopped the timer too quickly, or it could be that they misread the timer, or they started the timer late, but essentially the recorded time taken is too short. Now, question 5 is about the magnetic field generated around a current carrying wire, and this is on page 229 of your revision guide. So it says, it shows us the magnetic field around a copper wire carrying a current. What do the arrows represent? Very simple. The arrows show the direction of the magnetic field. And then we complete the sentence. As the distance from the copper wire increases, the magnetic field strength does what? Again, this is given directly in the revision guide. The closer you are to the wire, the stronger the field is. So if we're going further away from the wire, then the magnetic field strength decreases. Okay. Suggest how the field lines show the variation in field strength. So notice that the concentric circles, they're very close together when we're close to the wire, and they're far apart when we're further away from the wire. So the distance between the magnetic field lines shows the change in field strength. That would get me 1 mark. Yep. And to get the second mark, I'm going to say the distance is smaller from this first part. We can see that they're smaller when it's close to the wire, when the field is stronger. Okay. And then it says he's now made his copper wire into a coil, okay, and measured the strength of the magnetic fields inside the coil. So we've got number of turns on the coil on the x-axis, and on the y-axis we've got the strength of the magnetic field. So we've got number of turns against strength. So the first task we had to do was draw a line of best fit. Now, when you're asked to draw a line of best fit, in some cases, remember, a line of best fit could be a curve, but here we can see that this looks like it's going to be a straight line. When I've got no turns, so I've got no wire, there's going to be no magnetic field. So I'm going to draw my line to pass as much as possible in between the points. And I draw a single thin straight line, like so. So it's passing through most of the points. This one's slightly below, this one's slightly above. So I've got the same number above and below. That gives me a good line of best fit. Then says, determine the increase in strength of magnetic field when the number of turns on the coil is increased from 12 up to 18. So on my graph, I can go up, that's 11 and that's 12. So 12 is here, and that is a value of 0.9. That's 12. It's a good idea just to always draw in the lines like so, and the end value is 18. That's 19, that's 18. There I have 18, goes up to there, which gives me a value of I've got roughly a value of just over 1.3 roughly. Okay, so from the graph the magnetic field strength, change in magnetic field strength is equal to 1.3 minus 0.9. I check my units on what's written on the graph, and it says in arbitrary units. So the increase in magnetic field is going to be equal to 1.3 minus 0.9, so that's 0.4 arbitrary units. So that's 0.4. How could the strength of the magnetic field be increased? This is the magnetic field that's through a solenoid, and that can be increased in one of three ways. We can increase one, the number of turns, two, the current, and three, we could add an iron core. Okay, so let's see which of these is there. Increase the potential difference, that's not one. Increase the temperature, no. Spread the turns of the wire further apart, no, that's not it, as long as we've got the same number of turns. Use wire with high resistance, no. So increase the current, this is the one we want. Final two parts. Figure 3 shows the north and south poles of a solenoid. Draw the field lines. So remember, as I said before, if we have to draw the magnetic field around a coil, it's as if we're drawing a bar magnet, and we do the same thing. I would draw at least 2 loops on each side, with the arrows going from north to south, and so I'll do the same here. The only thing you must remember is to finish the loop inside the coil, like so. So inside the coil, they are all straight lines. They loop around outside the coil, like in the bar magnet, but inside the coil it's in a straight line. And I need to show the arrows going from north to south. How can a solenoid be made into an electromagnet? So this is the definition of a solenoid. A solenoid with an electromagnet is called a solenoid with an iron core is called an electromagnet. So how can I change it into an electromagnet? I need to add an iron. So question 6, and once again what we see is the first question is showing us the magnetic field, and we're asked to show which one is the correct magnetic field around a bar magnet. If you notice these two here the magnetic field is not touching the bar magnet. Now this would be the magnetic field around a current carrying wire, so these two answers are put in there to try and make you confuse the magnetic field around the wire with the magnetic field around the bar magnet. The magnetic field around the bar magnet has to come out from the North Pole and go round into the South Pole. So we can see that these two, the magnetic fields aren't even touching the pole, so these two are definitely wrong. With these two, it has to show the arrows going from the north to the south, so the answer is going to be this one. Okay, and then question 6 part B. We're shown 3 blocks. We're told that one is a permanent magnet, one is iron, which means it's made from magnetic material, and one is aluminium, which is non-magnetic. And we're given a second permanent magnet and asked to identify the blocks. So if this block was aluminium and we brought the permanent magnet up to this block, nothing's going to happen. It's not going to be attracted, it's not going to be repelled, because it's non-magnetic. So we can say the first thing is the permanent magnet has no effect on the aluminium, and we'd know that's the aluminium because there's no effect. If it was brought up to this one and this one was the iron, no matter what way round we had our permanent magnet, if we brought the North Pole towards it or the South Pole towards it, in all cases it's going to attract this block, which means because it's always attractive, it must be magnetic material, i.e. this must be the iron. So we can say the permanent magnet in any orientation always attracts the iron block. And then finally, if this one was the second permanent magnet, when we bring the permanent magnet up towards it in one orientation, for example with the North Pole, if that was the South Pole here, then they would attract. But if I brought it up towards it with the South Pole first, then they would be the same poles, so they would repel. So the permanent magnet can attract or repel the other permanent magnet, and that would allow us to identify them. So then the last part of this question, we're told here's an application of an electromagnet being used in a toy crane. And the key thing about this question is you should note that they ask us to explain how it's able to both pick up and move the blocks. So the toy has to be able to attract and lift up the blocks, and we then have to be able to move across, for example, to the other side of the table and place the blocks down and release them somewhere else. So we need to be able to attract and hold on to the blocks, and then we need to be able to release the blocks. Okay, so you see my answer is in two main parts. So to pick up the blocks, the electromagnet needs to attract the blocks. Okay, that's just, I open up by my little answer by starting with this statement, meaning that the electromagnet needs to be able to magnetically attract the blocks. So this first part is all about the picking up part. So this is done by closing the switch, completing the circuit, so that the current flows in the coil of the electromagnet to produce a magnetic field. So you see there's a switch shown in the diagram. When the electromagnet is moved close to the block, it will attract the block. And then the second part is about the movement part. Move the electromagnet and block together to the new position. Open the switch to stop current flowing in the electromagnet. As there is no magnetic field, the block is released, and hence it will be in a new position.